pleased to introduce the speaker for this session, Prith Banerjee. Prith Banerjee is the Chief Technology Officer of Ansys, where he is responsible for leading the evolution of Ansys' technology strategy and champion the company's next phase of innovation and growth. Formerly, he held executive positions at Schneider Electric, Accenture, ABB, HP, and HP Labs. He has also served as the Dean of College of Engineering at the University of Illinois at Chicago and taught at Northwestern University and the University of Illinois at Urbana-Champaign. In 2000, he founded ExcelChip, a developer of products for electronic design automation, which was acquired by Xilinx in 2006. And in 2005, he founded Banerjee, a developer of products in electronic design automation, where he served as chairman and chief scientist until 2011. He is a fellow of the AAAS, ACM, and IEEE, and a recipient of the 1996 American Society for Engineering Education Terman Award and the 1987 NSF Presidential Young Investigator Award. He received a B.Tech in Electronics Engineering from the Indian Institute of Technology, Kharagpur, and an MS and PhD in Electrical Engineering from the University of Illinois, Urbana. It will now be our pleasure to hear from Prith Banerjee.
Hello and good morning. I'm going to speak today to all of you about the use of AI/ML, HPC, and AI machine learning in engineering simulation on the cloud. So let's begin. But before I begin, I want to kind of briefly introduce myself. As I said, I'm CTO at Ansys. I've been with the company about 4 years. Previous to Ansys, I spent about 20 years in academia as a professor, a department head, and a dean of engineering at the University of Illinois and Northwestern. And then I spent the last 15 years in the corporate world, first as director of HP Labs worldwide, as CTO at ABB and Schneider Electric, and 4 years ago joined Ansys. In my role as CTO at Ansys, I'm responsible for setting our long-term technology strategy around areas such as HPC, AI/ML, and cloud, and this is what I'm going to talk to you about today. So today I will provide a quick overview of Ansys and our long-term technology strategy, and then go deep into the discussion of AI/ML and high-performance computing and simulation on the cloud. So Ansys has been using the power of simulation to help customers build amazing products in different verticals. For example, we work with Airbus in the aerospace and defense area. We work with customers such as Magna as a tier one supplier in the automotive area. We work with Medtronic and Boston Scientific in the healthcare area. We work with LG in the high-tech area. And we work with customers such as Schneider Electric in the energy area. In terms of partnerships, we have very strong partnerships with a lot of companies, including Rescale. Thank you, Rescale, for inviting me to speak today at your Big Compute conference. But we are partners with all the chip companies such as Intel, AMD, and NVIDIA. We are partnered with all the cloud companies, such as Microsoft Azure and AWS, and customer and partners such as Autodesk and Synopsys. So this slide kind of talks about a very broad overview of our Ansys product portfolio. The bottom of the pyramid, you can see our core solvers, such as structural analysis using finite element analysis for mechanical, such as Ansys Mechanical or LS-DYNA. Fluid simulation products such as Fluent using finite volume methods. Electromagnetic simulation such as Maxwell for low frequency or HFSS for high frequency. Semiconductor simulation for power integrity, such as Red Hawk SC, optical simulation, photonic simulation, and so on. So those are the core physics simulations that we have to offer with our customers. And on top of those physics simulation, we have software simulation capabilities using tools such as SCADE for embedded software, and Medini for safety analysis, and Twin Builder for digital twins. And then we have a platform using sort of materials platforms for Granta for materials, optimization platforms such as OptiSlang, and we do all of these multi-physics simulations on top, leveraging HPC on the cloud. We take our simulation solvers and we have built out entire solutions for autonomy, electrification, 5G, and industrial Internet of Things. And we serve more than 40,000 customers in the verticals of aerospace and defense, automotive, energy, healthcare, and high tech. So, as CTO at Ansys, I am responsible for setting our long term technology strategy. And that has 12 pillars that I'm going to mention here. Pillars such as numerical methods, where we are looking at more accurate, faster, easy to use, and robust solvers, looking at newer methods for meshing and geometry, the use of AI, ML applied to simulation, high performance computing, leveraging different forms of parallelism, uh, new ways of doing user interface and visualization, different types of platforms, use of the cloud. We have an entire work on developer ecosystem and solutions, model-based systems engineering, digital twins, integrated ICME and sustainability, and healthcare. So today I'm going to focus on three of these topics on HPC, AIML, and the cloud. So let's begin. So in the area of HPC for simulation, uh, we have a lot of solvers. Our core solvers, such as Fluent, Mechanical, Numerical, LS-DYNA, we are exploiting parallelism at different levels. At the highest level, we explore parallelism. We do parallel parametric analysis. Suppose you want to use design of experiments using our OptiSlang platform, and you are running maybe 1,000 different variants. Those are independent parallelism where we use HPC job scheduler to exploit the parallelism. The next level for a particular solution, we use domain decomposition where we break up a problem into different domains. Each domain we send to a processor, and we have message passing that is sharing information across different processor clusters. Within one domain, we can use multi-threaded parallelism or shared memory parallelism to get some speed ups. And in the finest grain, we use GPU-based parallelism, or SIMD parallelism, or TensorFlow for the Google platform. So, in summary, we are using parallelism across all forms, across all our solvers. Just to give you an example, our Fluent software is the most commercial grade CFD software, one of the most high performance software out there. And what this is showing is how we are able to use domain decomposition to break up a fluids problem into different domains. As a fluid is flowing from the left hand side to the right hand side, we break it up into different domains. Each of those domains are sent to different processor clusters, and the processors share information across using MPI. Within each domain, we are using shared memory parallelism, and then within that, we are using also GPU-based parallelism. So, result of this is Fluent runs scalably across 200,000 cores on both on-premise HPC as well as on the cloud such as Rescale. So that's the first example. Second example is that of LS-DYNA. This is our premier crash simulation software. And so what this is showing is using explicit methods, and this is showing how LS-DYNA scales using a Rolls-Royce engine model as a representative model and running on a Cray machine on an Oak Ridge National Lab, the Titan machine. And this is showing a problem. The engine model has more than 200 million points. And what this is showing is how this is provided scalable speedups going from 512 MPI ranks, clusters, to 8,000 clusters. And in each cluster, we are running sort of shared memory parallelism with 8 threads per rank. So this is a combination of MPI and shared memory parallelism. And the different curves are showing different types of partitioning that we have used, with the max cart partitioning, the min cart partitioning, and the original first partitioning. Again, showing scalable speedups for LS-DYNA up to 8,000 clusters. The third example I want to show you is our work on Ansys Discovery, which is a software that has been written from scratch to take advantage of fine-grained parallelism on the GPUs. And we have taken the structural physics, the modal physics, the thermal physics, the electrothermal, and essentially getting it to run scalably on lots and lots of sort of the threads of a GPU. And this is showing it allows us to get instantaneous simulation as you are entering a new CAD design on a CAD tool. It gives you instantaneous simulation about the design changes. Now we took that core solver from the fluid solver from Discovery, and we have recently this year integrated that into a work on a multi-physics fluid solver, which is Fluent. And so essentially, in the Fluent example, I showed you how we are using domain decomposition to take a partition, to take a problem and break it into different partitions, and I have each partition go into a processor. What this is with the same approach, but it's going to each of those regions going into a GPU. So this is a multi-GPU implementation, leveraging the fluid solvers in the Discovery software. So the results on the right are showing how this multi-GPU solver is showing speed ups of up to 32 times using an 8 GPU NVIDIA A100 card. So this concludes our quick review of HPC. Now let me kind of focus on the use of AI, machine learning on simulation. Now, when we've looked at AI/ML, we've kind of looked at sort of two broad approaches. One is a top-down approach where we use the solvers as a black box and an optimization platform such as OptiSlang, where you're using maybe 1,000 different runs to run a particular design, right, in 1,000 different variants, and typically each run would take maybe 100 hours. So the whole runtime would take 100,000 hours. What we are doing with the AI/ML is to take the first 100 runs of the design of experiments and use it to train the AI/ML models. In the remaining 900 runs, you are using the neural network based fast algorithm. And so what this is showing is how we have combined OptiSlang with the IcePack solver for thermal modeling to get a thermal meta modeling which runs sort of hundreds of times faster. We have combined, the bottom left is showing how OptiSlang has been combined with RedHawk-SC, which is a power integrity tool for power integrity meta modeling. And then the bottom right is showing how we have combined it with HFSS to do electromagnetics meta modeling. While these top-down methods work well for the specific use case that you're doing the design of experiments for, if you're trying to do a general purpose fluids problem, then you have to use a bottom-up method. And what this slide is showing is our ML solver for partial differential equations, for the fluids equations, for Navier-Stokes equations. And this is showing how essentially you take a problem and you break it up into an 8 by 8 by 8 or a 16 by 16 by 16 region. And for that region, you try to solve the fluids problems. Based on the fluids problems, you try to train the neural network. So that's sort of what you're doing with the encoding. You're taking a higher dimensional problem, mapping it into a lower dimensional solution, using that to learn what is in the fluids physics, what's in the Navier-Stokes equations. And then essentially you can take that and essentially just like normal iterative methods, you sort of take the single solution patch and you move it across to the right-hand side, and you build up the full solution. So this basic idea of a ML-based solver was initially done for steady-state solutions, then for transient solutions, then for regular meshes, irregular meshes. And the picture on the top right is showing how we have solved the external flow use case for airflow over a car, and you have integrated with Fluent, and this gets a speed of about 100 times more than Fluent for the same accuracy. So very, very exciting work on bottom-up methods. The same bottom-up method we have applied to solving electronic chip package simulation problems. And what this is showing is when you have a large chip, maybe a billion transistors on the chip running at 2 gigahertz, it generates hotspots in the chip. And so typically, and then you have to, in order to do the chip thermal and the cooling of the chip, you have to use our Ansys mechanical tools working with the RedHawk-SC and then doing the IcePack to do the whole fluid flow, the air cooling or the water cooling. What we are doing with this AI/ML approach is to essentially train the mechanical and the IcePack models, right, using the neural network approach, and it runs it much, much faster, about 100 times faster. We have also used this ML-based method for hotspot detection to, as we are showing here, right, for the 10 by 10 micron region or 100 by 100 micron region, the run times go from 4.5 hours to 9 minutes. So very, very exciting work on, again, a bottom-up method for chip thermal. The third example I'm going to give is in the resource prediction problem, When you're submitting a simulation job to a cloud, for example, a Rescale cloud, customers are interested how much runtime will I need, how much memory will I need, because obviously the customers don't want to be surprised with the runtimes and the memory requirements on simulation. Now, it turns out this is a very, very hard thing to predict, right? When you're submitting a structural simulation job on the cloud, right? You can do it based on the size of the unknowns, right? So is it 100 million mesh points or 10 million mesh points, 100 or 1,000 million mesh points, right? That's one of the things. The other things are the actual finite element method FEM features, right? So essentially, we have done a lot of work on data cleansing, data balancing, looking at through our Ansys product information program API. We can collect a lot of data on on our solvers running on premise or on the cloud, and essentially using that, we are training these neural network models, and based on it, we have launched just a mechanical resource prediction feature this year, and essentially what the results are showing is our memory predictions and our time predictions are very, very accurate, right? If you look at the excellent and the good, the combination excellent good is more than sort of 60%, which is very good. Now, what we are doing is now collaborating. We acquired a cloud stack called OnScale, and we are in the process of incorporating these ideas within our OnScale platform. Now, let me talk about our work of use of cloud in simulation. And in that, we have taken this large set of simulation software that I kind of talked about in slide 2, our structural solver, our fluid solver, electromagnetic solver, and all of the solvers are now, we have provided a Python interface and to run on the cloud. And so essentially all these solvers are running and location independent, using unconstrained HPC on the cloud. And on the top, what we are showing is we are providing these Python interfaces to allow developers, engineers, and professionals to build personalized solutions to solve problems like noise, vibration hardening, or healthcare applications, or different types of things to solve very, very interesting engineering problems. So this is sort of the journey towards a developer ecosystem. Now, our cloud journey is kind of talked about here. Obviously, we have been partners with Rescale for the last many, many years. And with Rescale, all our solvers are running using a SaaS-based platform, right, on Rescale on various clouds. But in addition to the partnership with Rescale, we've got some other efforts going on in the cloud. The left side is showing how we are using a containerized marketplace to make sure that each of our solvers, our customers can take the HPC licenses to our solvers like Mechanical or LS-DYNA or Fluent and run it on their favorite cloud, be it Amazon, which is what we have got it working. In fact, this month we got it running with the Amazon marketplace for the cloud, and we will have future versions of this with other cloud partners. The right-hand side is showing is how we are moving towards, since we acquired OnScale, we now have the capability for a full SaaS-based cloud offering, a cloud-native offering to recall each of our solvers are Mechanical, Fluids, HFSS, and running them on a SaaS-based manner, right, based on sort of users and running it on a cloud in the backend run by Ansys. So we are providing all three forms of the cloud: Rescale cloud, the sort of cloud marketplace, and a SaaS-based cloud. I want to end my presentation on the sort of direction of this pervasive insight that we have created, right, with this Ansys framework. So what this has done is we are providing a Python interface to all our products, all our solvers like Mechanical, LS-DYNA, Fluent, and so on. And what this Ansys platform, which is an open platform, does is to allow our customers, right, and developers to build different solutions, like, for example, a noise vibration hardness application, or a healthcare application like a heart model, or a healthcare application like a bioreactor digital twin, in a very easy to use, seamless way to build different solutions. And so we are building different types of solutions as a SaaS offering on the cloud. And we are in a sort of 5-year transformational journey for all our Ansys products, where we are trying to drive towards more cloud adoption by providing these products as SaaS-based products enabled by a Python ecosystem. And so, in summary, what I wanted to kind of share with all of you is we are excited to partner with Rescale in the area of sort of product-based innovation. Simulation is used as a way to innovate new products, and simulation is at the center of virtual prototyping, where people are moving away from hardware prototyping and testing to software prototyping and validations and virtual validation, and it's enabled through simulation running on the cloud. So simulation allows our customers to grow both top line revenue and bottom line savings. It allows our customers to do a lot more rapid innovation, lowering cycle times and lowering risks. Hopefully, you have understood that Ansys provides a very broad and very deep simulation platform in various industries such as automotive, aerospace, high tech, energy, and healthcare. And what in this presentation, what I've been able to show is a couple of areas of our long-term technology strategy. One around HPC, second around AI/ML, and the third one is around the cloud. Thank you very much for your attention.